This video note is on section 15.2 in the textbook on curves and line integrals, and there's also the concept of arc length, which comes in this section, which is very important too. So you might have actually included that in the title. So we begin with the concept of arc length. So arc length. So we know from chapter 14 that a curve is some vector r as a function of time. And I can define the arc length along that curve between two times. So the arc length s as a function of tau, which is some time, is going to be the integral from some arbitrary initial reference time to the time tau it's going to be a time integral of the speed. So the speed is the magnitude of the velocity vector, so that's r dot product with r dot, and I need to integrate that with respect to time. Okay, so again, let me write the words. So the arc length is the integral of the speed. The speed is the magnitude of the velocity with respect to time. Okay, so we can also reparameterize these curves. So if I let t go to some function f of t, and I write r as a function of f of t instead of t itself. So I'm, like I always say, Steve Miller, time keeps on slipping into the future. I can go at a different speed as long as this f is monotonically increasing. Okay, so maybe my clock is ticking slow originally, so this could be f as a function of time. So my clock is ticking slow, and then eventually my clock is ticking faster at the end, and I'm going along that curve faster than I would be if I'm treating it as a function of f rather than treating it as a function of t. And so I still have that s tau is the derivative from tau naught to tau of r dot, but r dot is equal to, we know from before, from chapter 14, we can just use the usual chain rule. So this is going to be dr, I'll call it r prime, which is dr df times df dt. So this expression here is going to be integral of r prime dotted with r prime, and then I pull out a factor of df dt with respect to time. So what you see happens here is that my integral, I can think of writing that as an integral not as a function of time, but an integral as a function of this new parameter f, right? And so I go from my initial value of f to my final value of f, and this is r prime, which is the f derivative, r prime, that's the f derivative, and we see those guys cancel out. So I can really think of this as being a function of f rather than a function of time, but the functional form is precisely the same. Okay, so I can reparameterize. If I march along a curve, it doesn't matter if I march slowly at the beginning and quickly at the end, or if I were to march along the curve quickly at the beginning and slowly at the end, so time is going slower, or f is increasing more slowly at the end, so I'm marching along that curve more slowly as a function of time. Doesn't matter. I still get the same arc length because of this cancellation right there. It's a very important cancellation. So I can think of this arc length as not really being dependent on time per se. It's a property of the path, not a property of how fast I move along the path. Okay, so let me give a quick physical example. This is not in the textbook, but I think it gives some insight. Let's suppose that I have a projectile that I launch from the roof of a building. Okay, and we know from high school physics that this projectile will follow a parabola. So Newton's second law tells us that F is equal to ma, but F is equal to minus mg in the j hat direction. So as usual, I hat is horizontal, j hat is vertical, and so I can break that acceleration to Cartesian components, and so this tells me that mx double dot is equal to 0, my double dot is equal to minus mg. The m's go away, so this tells me that x dot is equal to a constant. So x is equal to v naught, the initial velocity, times time. And so this tells me that y dot is equal to minus g times t. I'm assuming that there's no initial y velocity, and so that tells me that y is equal to minus 1/2 g t squared plus the initial y value. Let's say that's my origin, and the height of the building is L. Okay, and it leaves with a horizontal trajectory. So now I have x and y as functions of time. So if I want to know what the arc length is, how far, not vertically or horizontally, but if I want to know how far did the ball travel along that parabola, well, I have to integrate the speed. So just doing some dimensional analysis, well, I won't do the dimensional analysis yet. Let me just write an expression for the speed. So the velocity v, which is equal to the time derivative of the position, that's x dot I hat plus y dot j hat. So the magnitude of the velocity, which is the speed, that's just x dot squared plus y dot squared square root. So I have my expression for, let me actually write v naught for my horizontal velocity. So I have my expression for the horizontal velocity. I have my expression for the vertical velocity. So I know the speed. So this is equal to square root of v naught squared. That's the horizontal velocity that I use to throw the ball off the roof. And then I need my plus g squared t squared. So the horizontal velocity is always v naught. The vertical speed is g times t. And so the total speed is square root of v naught squared plus gt squared. So there's one piece that's a constant. There's one piece that depends on time. And so now I need to figure out what the total distance traveled along that parabola is. So the arc length s is going to be the integral from time equals 0 to time equals t max. For the moment, let's just leave that upper limit of the integral as a parameter, and we'll figure out what t max is in a moment. And so the thing that I have to integrate is the speed with respect to time. So that's v naught squared plus g squared t squared integrated with respect to time. I look up in my favorite computer program, I use Mathematica, and it tells me that that's t m times, let me call it t max, times v star, I'll define v star in a moment, divided by 2, plus v naught squared over 2g times the log of g squared plus g times v star. Okay, so just using dimensional analysis, I can look at the parameters in this problem, and there is a characteristic velocity that I can form, v star, which is v naught squared plus gt max squared. And I can define T max. T max is just the time that it takes to fall. Okay, and so that's how long does it take to get from y equals L to y equals 0, and T max is equal to the square root of 2L over G. Okay, so if I put in, using dimensional analysis, these two constants into that expression, that will give me the total arc length. So now I just want to say one word about averages. So I can ask, what was the average height of the ball? This is a very interesting philosophical point. So average. When you use the word average, you have to be very careful and ask if you're interested in the average over time or interested in the average over what. So in this case, there are at least two things that would make sense if I just ask about the average height of the ball. I could mean, so let me write this, at least two things. So first, I could just mean the average over time. So for instance, if you were had a stopwatch and you were sitting on the ball, and every microsecond you made a measurement of your height, and you averaged those measurements of your height when you were taking them at equal intervals in time, the calculus expression for that quantity, which I'll put a bar on top, the average, the time average y value, would be the duration of the free fall. That's I'm dividing by the duration of the free fall, which is t max, integrating from time 0 to time t max, and I'm integrating y. So this is a time average. When I integrate some quantity with respect to time, and I divide by the total time, that's the time average of the quantity. Okay, and we could actually figure out what that is because we have an expression for y of t. That's just 1 over t max integral from 0 t max of L minus 1/2 gt squared dt. I'm not going to do that integral. We could. We know what t max is. We know what everything else is. So we could find the time average height of the ball. Okay, but usually and this the definition of a line integral follows from this idea. We want the average not over time, but over arc length. Over length ds, not time dt. So we want to integrate with respect to length along the path. So the second definition, which is what I would argue is the correct one, and we're using to set up this notion of line integrals in chapter 15.2, is we want y, and I'll put, instead of using an overbar, sometimes in statistics we use these angular brackets, right? So this is an average, not over time, but over distance along the trajectory. So now if I'm sitting on the ball and I'm making measurements of the height and I want to define an average, whereas before I was using a stopwatch to figure out how often I should make measurements of height to average together, here I would be making measurements of distance. And so every time I traveled 1 centimeter, I would read off the height that I was at, and I would average those numbers together. So this is an average over length traveled along the path. And so that's integral of 1 over the total length along the path, 0, to the maximum arc length, y of s ds. Now, what do I mean by ds? Well, the speed, ds is a little bit of arc length that gets played out along the path, right? So if I were to draw this path, so here's my baseball cascading down. So if I were, so I know at the end of the day I have to make a parabola. Trying to draw a parabola, I'm sorry. There's my parabola. So if I'm drawing this equally spaced in time, at the beginning I'm going slowly, and at the end I'm going more quickly. So this is what it would look like if I was evenly spaced in time. As opposed to what would happen if I was evenly spaced in distance. Dot, 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 dot. So even though the ball's going faster, my points aren't any further spread out. So this is even in distance. Okay, and so the distance between these 2 points, let's call that ds. And so we know, well, what's the distance that I travel in a given unit of time, that's just the speed. So this is square root of v dot v. That's the magnitude of the velocity vector. Okay, and so let me call that s dot. So that's the time derivative of the arc length along the path. And so I can go in and I can rewrite that expression using a change of variables. That's the integral of 1 over the path length, integral from 0 to, now I'm switching to a time integral. So this is to t max, and really I'm integrating y as a function of time times the speed, which I can say that's the magnitude of the velocity vector, times dt, right? Because ds is really, let me use a different color here, ds is really the speed times dt. So I'm just doing a change of variables in the integral, and I'm writing my average of s over the path as an integral over time, but it's still the average of s over the path length. Okay, and so for our problem here, we have y as a function of time, and I can simply write the answer. So that's 1 over the total path length, which we computed in the previous part of the problem, and I need to integrate the height times the speed, and the height is L minus 1/2 g t squared. The speed is v naught squared plus g squared t squared square root. I'm integrating that thing with respect to time. So this is the average height when I'm averaging over the distance traveled along the path. Okay, and so that is our definition of a line integral of a quantity. It's actually the definition of a, I'm sorry, that's not the definition of the line integral of quantity. That is the definition of an average, but we can quickly write that as, in the future, I'm sorry, I shouldn't have brought up line integrals at this point. Let's hold off on that. So now I'm going to end the video, and we'll do an example in a separate video note.